Welcome, everyone. My name is Deirdre Haskell, and I'm the Deputy Director of the Fields Institute for Research in the Mathematical Sciences, and I'm also a Professor of Mathematics and Statistics at McMaster University. What I want to talk to you today is called What is Behind the Numbers? And the point is that I want to tell you something about the models that we've all been hearing so much about, these models of COVID-19, and we've seen lots of graphs, but it's not so clear, or what I would like to explain to you is what the model is, and what does it mean when we say somebody's doing modeling. And when you're really doing modeling, and the modeling that we're seeing and the graphs that we're all seeing about COVID-19 are very complicated models, and they have real data in them, and those real data is complicated. And so it becomes hard to understand what the picture is. You can't see the wood for the trees. There's too much detail. And so what I want to do today is to get rid of some of the trees so that we can see the bigger picture a little bit more clearly. So that means I'm choosing to deal with the very basic model, which underlies the more complicated models that people are using. And I'm also using very straightforward numbers, which are easier to deal with. And I do hope you all brought a calculator so that you can actually get them out and do some number crunching, so we can just see that actually we can, just from the very basic model, we can actually see what's going on. So the particular question that started me on this was somebody asked me shortly after Easter, why are the case numbers still going up even though people are getting vaccinated? Doesn't the fact that people are getting vaccinated mean that the numbers should start to go down? And so I want to look at numbers which will illustrate what's happening and why those numbers continue to go up, although there's hope also. They don't have to continue to go up. We can see them coming down again. So here's where let's get started, okay? So let's look for the basic model. So the quantity that we're interested in is what I'm going to call I, is the number of people who are infected at any particular time. And that number could go up over time. So if I draw a graph of it and just see that the number could go up, or it could stay constant, or it could go down over time. Sorry, those are supposed to be lines. It was just like my hands shaking a little bit. So that's just a very simple showing of how the number I might change. But if I draw it as a line like that, if the slope of that line is positive, it means that the number of people who are infected is increasing. If the slope is equal to 0, it means that the number of people who are infected is constant. Notice that I being constant does not mean that there aren't more people getting sick. What it means is that some people are getting sick and some people are getting well, or unfortunately dying. So the number of people who are infected at any one time is staying the same. So we have to keep that in mind as we go through this. But if the slope is negative, then I will decrease. And of course, that's the situation that we want to be in. We want that slope to become negative. So what tells us how this changes over time? And that's what it means when we start talking about creating a model for what's happening. So what we need to know are two key things: is the number of people who are infected and the number of people who are susceptible. So those are people who might become sick. And our basic model for how this changes is that the number of people who are infected increases because I have people who are susceptible and people who are infected, and they meet. And then because they meet and interact, then the disease passes. So how often do they meet? Well, that will depend on how many people I have here and how many people I have here. And the number of interactions is the product. I just take this number times this number, and that gives me the number of possible interactions. If I have 3 people who are sick and 2 people who are susceptible, then they can interact 3 times 2, which is 6. So I have the product. So the number of people who are infected will increase at a rate which is proportional to the number of people who are infected times the number of people who are susceptible. So at a rate which is proportional to means equals a constant times. So that's how the number I will go up, and the number I will go down because people get well or die. So the I will decrease at a rate which is proportional to the number who are infected. So that's those two key facts are what we put together to create the model. And so we say that the slope of the curve, which is the graph of the number of people infected against time, that slope will be equal to a constant, which I'm calling K1, times I times S, and that will be the way in which the slope is positive. And the way in which the slope goes down is we subtract another constant times the number of people who are infected. And those are those two pieces of information now written in an equation. So the slope of the curve is a constant times I times S minus a different constant times I. And that's our model. Now, what really makes this work is to work out what these two constants are, what values they should have. And that's the modeling process. That's how we look at, we say, well, this is our model. This describes what's going to happen. But what should these constants be? And for that, we have to look at real data. We have to say, well, what's actually happening? And so that's our modeling process, is to find those two numbers. Now, K2 is a relatively simple number. We can estimate that by saying, well, people on average will be sick with the disease for a certain amount of time, say 10 days. And so the number of people who get well in any one day, or the number of people who move out of this category in any one day, will be 1/10 times how many I have. And that number we can get, so we can try out this number 1/10 as a sample. This number K1 is really hard to work out because we need to know all this information about how many interactions are there between people in category I and people in category S, and how much of an interaction is needed in order to actually pass the disease, and are they wearing masks or are they not, and that will change what the value K1 is. So there's lots and lots of things that go into that. So finding that value is very much part of the modeling process. So what I've done here is to take a sample value for that number, and I've just called it 0.0005. That's a number which seems to give us a model which has some reasonable behavior that we can look at. I'm not in any way claiming that this is the real number. Okay, so then what that says is that our equation for the slope is that it's 0.005 times I times S minus 1/10 times I. So let's just try this out. Suppose we have a population which has 500 people who are susceptible, 25 people who are infected, and then what does that tell us about our graph? So now here's where you all get your calculators out. Okay, so in order to calculate the slope, we want to take 0.0005 times I, which is 25, times S, which is 500, and then minus 1/10 times I. That's easy to do. We just move the decimal point, so that's minus 2.5. All right, and I hope you all calculated away and got the answer 3.75. So that tells us that our slope is positive. People are very good, thank you. So we got more people are going to be getting sick. And so our graph at this point looks like this. Okay, so now what happens if we suppose that some of our people are vaccinated? So I want to look at this kind of at a moment in time to say, well, suppose we had, what we just did was we said, suppose we had 500 people susceptible, 25 people are infected. And so the slope of our curve is 3.75. And notice what that means is that the fact that the slope is 3.75 means that if we start here at 25, then after 1 day, the number of people infected will have increased by exactly the slope. So the new value of I is the old value plus 1 times the slope. So plus the slope, and that takes us up to here to 28.75. So we've gone up by that amount. So now what I'd like to look at is everybody, all of you, just choose one of these input data, S equals 400 or 300 or 200 or 100. So we're imagining here, suppose instead of having 500 people susceptible, I had vaccinated some part of my population. And so I have vaccinated 20% of my population, or 40%, or 60%, or 80%. And let's just see what all those numbers come out to be. And I'm going to fill in this table as you tell me the numbers. So did somebody do S equals 400? What value did we get for the slope?
2.5.
2.5. And so that gives us that the new value of I is 27.5. So with some people vaccinated, 400, my slope is still positive, but it's not as large as it was before. So my slope, my current graph here is increasing, but not as steeply as it did before. Okay, did somebody do 300? What's the slope? Somebody going to give you
You're furiously calculating.
Choose one and do it, and then we got there. Okay, thank you, Brian. 1.25. So that means that the new value of I is 25 plus 1.25, which gives me 26.25. So my slope is still positive, but not as large as it was. And so this would be, my graph is looking something like this. 200. Did anybody do 200? 0. Okay, so the slope is 0. So when we've got 60% of our population vaccinated, the slope is 0, and so the value of I does not increase. And so my graph is horizontal here with 0 slope. And just to complete the picture, 100?
Negative 1.25.
Negative 1.25.
I got
So,
that too.
Great, thank you. All right, so this means that in this very basic model that we're looking at, once 80% of the population has been vaccinated, 80% of the population is vaccinated, our numbers, our caseloads will start to go down. The number of people infected will decrease. And so that's kind of the situation we want to get into. But this still doesn't answer the question of why, what's happening kind of on a daily basis. I mean, here I just said, suppose that I start looking at my model with my number of people susceptible already at this number. But that's not what's happening. What's happening is that as we go from day to day, we get more people vaccinated, but we also get people getting sick. So the number S and the number I are actually interacting. So let's look at what that says happens. So just looking at as things are changing over time, remember that my equation is still that the slope is 0.005 times I times S minus 1/10 times I. But now I'm going to include the fact that I is changing because of this slope as I calculate what happens. So on day 0, I'm going to start with a population of 500 and a number of people infected is 25. And as we saw, the slope is 3.75. And so that gives us, after 1 day, we've reached a number of infected as 28.75. But now I go in, and on day 1, I vaccinate some of my population. So my numbers of susceptible goes down to 400. But also my number of people who are infected has gone up to 28.75, because that's what we calculated it to be. So now when I calculate the slope, I have to have S is 400 and I is 28.75. And then I can look and see what value I get for the slope, and hence my new value of I. And did anybody do it? I'm going to give you this number. Oh, 3.25. That's not what I got. Somebody do it again?
Is it 2.875?
That's what I got, 2.875. So you see, even with pretty simple numbers, it's easy to make mistakes. That's why we have computers doing these things for us. But it feels so much more concrete when you put those numbers into the calculator yourself. You feel like you really believe it, even when it wasn't necessarily correct. Okay, so what does that mean about our new value of I? Well, so the new value of I is we take the old value of I plus 1 times the slope, and that gives us the new value of I. And so that comes out to be 31.625. So what does this mean? So when I first did it, my slope was 3.75, and so we had this increase of 3.75 in that first unit of time. In the second unit of time, my slope is still positive, but not as large as it was before. So if I sketch that in my graph, it says that in the second unit of time, I'm going to go up. I'm still going up, but by not quite as much as I did before. The slope is less than it was. And then in the next day, I vaccinate more people. So my number of susceptibles goes down to 300, but my number of people who are infected is this new value that we found, 31.625. And so my slope is now, again, I calculate using the constant 0.005 times my new value of I, which is 31.625, times my new value of S, which is 300, and then I subtract again the number of infected. And if I calculated this correctly, this comes out to the slope is 1.581, and then the new value of I is 33.21. So again, what's happened is that the slope is still positive, so my numbers of infected is still going up, but again, less than it was before. And if we do it one more time, on day 3, I have 200 people who are susceptible. My number I infected is this 33.21, and calculate the slope. And this time I got a value of negative 0.0004. So now finally, my numbers are starting to come down with a very slightly negative slope. But notice that one thing that's happened here is that we had our numbers of people infected were going up. We're going up until we got to the point where we had 60% of our population vaccinated. So that's why, even though people are getting vaccinated, the number of people infected is still going up, right? And so I see that my curve is going up, but going up more slowly. So the rate of increase is going down. And so that means that what we're doing is what's the term that people are using? We're pulling down the curve, so that even though it's going up more slowly. That's what we're seeing happening right now. Right? We're going up more slowly, so we're starting to get to the point where we can bring the curve down. But another thing that I want to look at here is what happens if we change this constant of proportionality, K1, right? So over Easter, lots of people were getting careless. We're getting together, we're having family gatherings, maybe not wearing their masks as much. And so suppose that what happened is that K1 actually doubled. So it became 2 times the value it was before, which gives us 0.001. So what we're doing here is just saying, suppose we're getting more people interacting, more infections. What does that do to our model now? So in this case, again, we have the same situation, we have the same slope equation, but now I've changed K1. So my slope now is going to be 0.001 times S times I minus 1/10 times I. So let's see what happens again, starting from the beginning. 500 people are susceptible, 25 people are infected. We multiply those two together, and we get the value, I hope you're getting the value 10 for the slope. Okay, so now what's happening, let's draw a picture of this situation. We're starting out with some number of people 25, and then the slope is 10. So that means we add, in 1 unit of day, we add 10 more people get infected. So that's a really steep curve. And so my new value of I is 25 plus 10, which is 35. On day 2, I've vaccinated some people. I have 400 people are susceptible, but my new value of I is 35. And I run through my calculation again of the slope, and I end up with my slope is 10.5. So I vaccinated a whole bunch of people, but because so many people got sick, my slope has actually increased instead of decreasing. And so that's giving, it's almost the same, but it's still just a tiny bit more. My numbers of infected is going up like that. So then my new value of I is 10.5 plus 35, so that gives me 45.5. And now I inoculate, I get another 100 people vaccinated, but my value of infected now is 45.5. And so my slope, again, 0.001 times S times I minus 1/10 times I gives me 9.1. So I've decreased my slope a little bit, but I'm still going up with a lot of people getting infected. And so my new I value is now 54.6. All right, well, I vaccinate another 20% of my population, and my value of I here is 54.6. I do my calculation to get the slope, and it ends up to be 5.46. Wow, that's a relief. It's starting to come down. The slope is, the value of the slope is smaller, so I'm not increasing quite as fast as I was before. And so I'm still, more people are getting sick, but not as many more as before. And that gives me my new value of I is 60.6. Now I'm down to 80% of my population is vaccinated. I have my value of I is 60.6, and my slope, anybody want to do this one? Yes, 0. Wow, finally. Okay, so notice that it took us 5 units of time to get down to that 0 slope, but look at the pain that we suffered while trying to get there. We got that many people, so many more people were getting infected in that time. And this is why we need to keep this number small, so that in the process of getting enough people vaccinated so that we can kill off this disease, we don't have to suffer this kind of pain in order to get there. So thank you for listening.